Hello, in this video we're going to look at the stationary distribution of ergodic Markov chains once more. We are going to show that these types of Markov chains have an underlying stationary distribution, but we are going to do it via a slightly different route this time. I think it is useful to present these demonstrations two different ways, as with this second derivation it is clearer precisely why we calculate the stationary distribution by finding the top eigenvector of the transition matrix. Before we get into the details of this proof, let's just briefly review what we have covered in the previous video with a little problem. I would like you to pause the video and draw the transition graph for a three-state Markov chain for which all the transition probabilities in the transition matrix are positive, i.e. non-zero. I would also like you to state whether the states in this chain are transient or recurrent. Hopefully you should have drawn a transition graph something like this. In addition, you will have noted that all the states in this Markov chain are recurrent. It is in fact an ergodic Markov chain. Square matrices that have all positive elements, like the one for the Markov chain whose transition graph we have just drawn, have a number of special properties. These properties are listed in a long theorem known as the Perron-Frobeneius theorem. We are going to use a couple of these properties here. In particular, we're going to note that any square matrix with all positive, non-zero real elements is diagonalizable and has a unique largest eigenvalue. In addition, we are going to need to recall that if we take a matrix and multiply it by its inverse, we get the identity matrix, which is a matrix which has all ones for its diagonal elements and 0 for its off-diagonal elements. Let's now focus on this business of the diagonalizability of the matrix and explain the meanings of the terms in this equation. An eigenvalue of a matrix A is a solution of the equation shown here. This equation is saying in words that there exist certain eigenvectors, V, which, when you multiply by the matrix A, give you the eigenvector V back again, multiplied by a scalar constant lambda, known as an eigenvalue. In other words, all the matrix A does when it acts on the eigenvector V is scale the length of this vector by a factor lambda, the eigenvalue. Any n by n square matrix has a total of n eigenvectors and n eigenvalues. In other words, there are n eigenvector and eigenvalue pairs that can be inserted into the top equation on this slide. Eigenvalues and eigenvectors are used in a number of different mathematical fields as they make doing certain kinds of matrix operations, such as taking powers of matrices or inverting them, relatively straightforward. The reason for this is because we can decompose an n by n square matrix in terms of its n eigenvalues and eigenvectors using the equation shown at the bottom of this slide. In this expression, capital V is a matrix containing the eigenvectors of A in its columns, and V minus 1 is the inverse of this square matrix of eigenvectors. The capital lambda between V and V to the minus 1, by contrast, is a matrix that has the eigenvalues of A as its diagonal elements. All the off-diagonal elements in lambda are equal to 0. The top equation on this slide shows that each eigenvalue has a corresponding eigenvector, and this pairing is evident when we decompose an n by n square matrix using the equation shown at the bottom of the slide. The eigenvector in the first column of V, capital V, has its corresponding eigenvalue in the 1, 1 element of the diagonal matrix lambda. Similarly, the eigenvector in the second column of V has its corresponding eigenvalue in the 2, 2 element of the diagonal matrix lambda, and so on. In theory, we could place the eigenvectors in lambda and V in any order we choose. By convention, however, the eigenvalues and eigenvectors are usually ordered based on the sizes of the eigenvalues. In other words, the largest eigenvalue of A is placed in the 1, 1 element of lambda with its corresponding eigenvector in the first column of V. The second largest eigenvalue of A is then placed in the 2,2 element of lambda with its corresponding eigenvector in the second column of V, and so on. As we shall see, eigenvalues and eigenvectors are useful in the context of stochastic processes, and as we can use them to calculate matrix powers quickly. Central to the ease of this is a result on the multiplication of diagonal matrices. Let's thus briefly look at the multiplication of a pair of diagonal matrices. If we begin by calculating the 1, 1 element of the product, we start as follows. We take the first row of the first vector and multiply it by the first column of the second matrix. We thus have lambda 1 multiplied by lambda 1, which is lambda 1 squared, plus 0 multiplied by 0, which is 0. To calculate the 1, 2 element of the product matrix, we take the first row of the first matrix on the left-hand side of this equation, and multiply it by the second column of the second matrix on the left-hand side of this equation. We thus have lambda 1 multiplied by 0 plus 0 multiplied by lambda 2, which is 0. To calculate the 2, 1 element of the product, we take the second row of the first matrix and multiply it by the first column of the second matrix. We thus have 0 multiplied by lambda 1, which is 0, plus lambda 2 multiplied by 0, which is again 0. To calculate the final 2, 2 element, we take the second row of the first element and multiply it by the second column of the second matrix, and thus get 0 multiplied by 0, which is 0, plus lambda 2 multiplied by lambda 2, which is lambda 2 squared. We thus find that we can multiply two diagonal matrices together by simply taking the products of the diagonal elements. Hence, when we need to calculate the powers of a diagonal matrix, we just calculate the powers of the diagonal elements. This is obviously much easier than conventional matrix multiplication. So we find that to square a diagonal matrix, we just need to square each element on the diagonal. We now have all the pieces we need to exploit the Perron-Frobeneius theorem to show that an ergodic Markov chain has a stationary distribution. The first step in doing so involves us remembering the Chapman-Kolmogorov relation, which tells us that we can calculate the two-step transition probability matrix by squaring the one-step transition probability matrix. Here I've called this one-step transition probability matrix capital A. We can write A squared as A multiplied by A, and then we can use the first part of our Perron-Frobeneius theorem to decompose each of these factors of A using the diagonalizability of a square matrix. We thus end up with the expression shown here. Notice that in the centre of the last term in this equation, we have a factor of v to the minus 1 multiplied by v. In other words, we have the matrix of eigenvectors multiplied by its inverse. But we know from the definition of the matrix inverse that if we take a matrix and multiply it by its own inverse, we get the identity matrix. We can thus replace the factor of v minus 1v by I. This gives us v lambda I lambda v minus 1. In the centre of this we have three diagonal matrices. But we've just shown that the product of two diagonal matrices can be calculated by taking the products of each of the diagonal elements in turn. We can thus replace the factor of lambda I lambda by lambda squared, which is understood to be a diagonal matrix with the squares of the eigenvalues along its diagonal. Obviously, this process could be taken further, and we could calculate higher powers of the matrix A in a similar way. If we wanted the nth power of this matrix, we would have a similar expression to that shown here. It would just have the nth powers of the eigenvalues along the diagonal elements of lambda to the n rather than the squares. We now need to consider the consequence of the second part of the Perron-Frobeneius theorem, which tells us that the matrix capital A has a unique largest eigenvalue. Now suppose I take the difference between the largest eigenvalue, lambda 1, and the second largest eigenvalue, lambda 2. This will always be smaller than the difference between the square of the largest eigenvalue and the square of the second largest eigenvalue. If you are not convinced, just stick some numbers in there. If lambda 1 is equal to 1 and lambda 2 is equal to 0.5, then lambda 1 minus lambda 2 is equal to 0.5, while lambda 1 squared minus lambda 2 squared is equal to 0.75. In addition, this is disparity between the nth power of the first and second largest eigenvalues is going to increase still further as we increase n. This is important as each of the terms in an can be thought of as a sum of eigenvalues multiplied by their corresponding eigenvectors. So each eigenvalue is multiplied by its corresponding eigenvalue, and then these quantities are summed. Each eigenvector is only ever multiplied by its corresponding eigenvalues. Now, when n is large, lambda 1 to the power n is going to be considerably larger than all the other eigenvalues. We can thus truncate all the sums in A and write the elements of A in terms of the product of the nth power of the largest eigenvalue and its corresponding eigenvectors, and its corresponding eigenvector. Furthermore, it turns out that because each of the rows in the transition probability matrix sum to 1, the top eigenvalue of the transition matrix is equal to 1, and all the elements of the corresponding eigenvector in the first column of V are equal to 1. As such, when we calculate a to the power n, we find that every row is equal to the first row in V to the power minus 1. To find the limiting stationary distribution, we thus need to only find the top left eigenvalue by solving the following equation with lambda equal to 1. The content of this video goes beyond what is required for this module. If you are interested though, you can work through the corresponding worksheets, and this will take you through some examples of how all the eigenvalues and eigenvectors of a 2x2 matrix are found. In addition, I also show on that worksheet that the problems in describing limiting stationary distributions for periodic Markov chains, like the one shown here, come about because they have multiple eigenvalues with the same magnitude. You need only go through this material if you are keen. Hopefully the video will have given you some sense as to why the stationary distribution is determined by finding the principal eigenvector, which is the most important take-home message for this video and within this module. Thank you.